Okay, so welcome to the third talk of this session. Great pleasure to introduce Dr. Arijit Chakrabarty. So his initial state was ISI Kolkata, where he did his BStat, then made a transition to Cornell for a PhD, then to ISC for a very prestigious postdoc position, then to ISI Delhi for his first regular position, by which time he started getting nostalgic about all the good fish and sweets. So made a deterministic transition back to Kolkata, and that's his absorbing state. So he has done many things, large deviations, heavy tails, random matrices, and today he is going to talk about clustering of rare events.
Thank you for the introduction. So I'll be talking about clustering of rare events, and this is a joint work with Gennady Samodytsky from Cornell University. This is perhaps the first and the only talk which is not related to graphs, but it's still peripherally related to networks, because I'll be talking about clustering in a way. So just okay. So the broad question that we try to address is, if and when a system deviates from its typical behavior, how likely it is to cause a sequence of subsequent deviations from typical behavior. So to make things a bit more precise, I start with a stationary process with finite mean. We look at the event that the sample of first n observations that exceeds the population mean by a fixed threshold. Okay, so epsilon is fixed positive number, and the question we ask is, given that this event has occurred, how likely it is for the subsequent sample means to deviate from the population mean by the same threshold. Okay? So this is nothing but the sample mean starting from xj, sample mean of n observations starting from xj. So this is broadly the question we'll be asking, and try to answer in a way. Okay, so this is a kind of a toy example. So consider an insurance company. Insurance company will of course fix the premium at a rate such that its expected return is positive. So now, if it so happens that at some point this becomes less than zero, then it would be interested in know the time point when till which it will continue to be less than equal to zero, or in other words, when it's going to make even. Okay. So the break-even point is essentially follows from this kind of questions that we'll be looking at. So as we all know, the study started with Kramer in 1938. So he showed that if you have the moment getting function, I'm just stated it in this way because in the next result, the assumptions are almost the same. If the moment getting function is finite, then the probability that it deviates is like e to the power minus n lambda star x, where lambda star is the central Legendre transform of the log moment getting function. So this is known to all of us. In 1960, Bahadur and Rangarao, Kramer's results studied the large deviation probability on the logarithmic scale. Bahadur and Rangarao studied it on a precise scale. That is, they showed that this probability is asymptotically like n to the n to the negative 1/2 correction times e to the negative n lambda star x naught. Okay, and this simply means that the ratio of the two sides goes to 1. So whenever in this talk I use this twiddle, it just means that the ratio of the two sides goes to 1, which is the usual interpretation. Okay. And then the study was furthered by Gartner and Ellis, which showed studied large deviations of some, so possibly non-identically distributed. Shaganti and Sethuraman kind of completed the square by studying strong large deviations which can be applied to non-identically distributed random variables as well. So, to the best of our knowledge, little is known about the asymptotic conditional distribution, given that one large deviation event has occurred. In other words, how do the events cluster given one of them? Yeah. Which is the question we try to address in this talk.
You'll be doing this in the Leiden setting?
Yeah. Okay. So before going ahead, let me go over the folklore, because I'll be using the words moderate deviation and large deviation. So if Z is the sum of several independent random variables, then a deviation of Zn from its mean by an order of the variance is usually called large deviations, whereas a deviation which is much larger than the standard deviation but smaller than the variance is called moderate deviations. So I would like to mention over here, I did not make precise what exactly Zn is and what are the independent random variables which add up to Zn, because it's just a folklore. So for example, if eta n is exactly of the order of the standard deviation, then this deviation is it's not a rare event, because the central limit theorem will kick in and show that Zn minus its expectation by standard deviation goes to none. So which is why for a deviation, it has to be much larger than the standard deviation. So there's an important qualitative distinction between large deviation and moderate deviation. Large deviation probabilities depend on the entire distribution, while moderate deviation probabilities depend only on the variance, because moderate deviations is in a way a continuation of the central limit behavior, which is why it's determined primarily by the variance of the. Okay, so now let's come to the problem that we are trying to address. So we are in the very light tail setting, that is, we have a stationary process with finite exponential moments, and I define by Ej epsilon n, that is, starting from J, the mean of the sample of size n exceeds the population mean. So mu is the population mean by epsilon. So it's even that the mean of the sample deviates from the population by at least epsilon. So for a fixed epsilon and large n, if we know that E0 epsilon n has occurred, how many of the subsequent EJNs are made likely by it? So now to make this precise, so let's say, regardless of whether this occurs or not, the moment we have this has a positive probability, this thing is infinity almost surely, simply because of ergodicity, nothing else. So in order to make sense out of this, make mathematically precise sense out of this question, we have to first look at j's which are small and then let that go to infinity. Okay, so therefore we have to first think about nearby Ej epsilon, that is, j is near to 1, 2, 3, 4, etc. And the answer, as we'll see, it depends on the memory of the process xn. Okay, so I have to tell you what I mean by memory. So let me first go to a Gaussian process, because memory is easiest to define for a Gaussian process. So a stationary Gaussian process xn is said to have short memory if the covariances are absolutely summable and the sum of the covariance is non-zero. Whereas it's said to have long memory if the covariance decays like n to the negative alpha for some alpha between 0 and 1. So this is the standard deviation of standard definition of short and long memory for a Gaussian process, and there are several reasons for that. One immediate reason is if you just compute the variance of the first variance of partial sum, then in the short memory regime, variance is like n, variance increases like n, whereas in the long memory regime, the variance increases much larger. That's one immediate reason. There are several other reasons. Okay. Now, we'll of course look at things beyond the Gaussian processes. We'll look at moving average processes. Okay. So we'll start with a collection of IID zero mean random variables with finite exponential moments. And these are coefficients which are square summable. AJs are coefficients which are square summable. And we use that to generate a moving average process. So this is a moving average process, J running from 0 to infinity, Aj, Zn minus J, where these Zn's are same over here, and mu is a fixed number, which gives the mean of this process. So Xn is the moving average process with input Zn and coefficients. And this is an ergodic process with marginal mean mu, of course, because these are zero mean. Okay. So in line with the definition that I gave for Gaussian processes, for moving average process, it has a short memory if the coefficients are summable and the sum of the coefficients is non-zero. Okay, exactly the same thing happens. The variance is like n. Variance of partial sum is like n. And on the contrary, if Aj is like j to the negative alpha, so remember now I cannot go beyond, I have to have the Aj square summable. Okay, so Aj is like j to the negative alpha for some alpha between half and 1, then it has a long memory, the process has a long memory. Okay, so let me first talk about the results we have in the short memory regime. So in this regime, the clustering is studied in 3 steps. So given E0 epsilon n, we study the behavior of the process indicator Ej epsilon n for j running from 1, 2, 3, etc. Okay, and we show that it has an asymptotic non-degenerate weak limit. That is, probability of each of the conditional probability of each of these, for example, converge to a number which is strictly between 0 and 1. I mean the results we have give a more detailed description of this process in the limit. Okay. But remember, these are for fixed j, 1, 2, 3, etc., and I let little n go to infinity. So for example, probability of E1 epsilon n given E0 epsilon n is, the limit of that is not the same as probability of E2 epsilon n given E0 epsilon. This is not the same.
When E3 is different from E2?
Yeah. We'll see. The moment we see the result, it will be very clear. Okay. So the once we have this, for any fixed k, we can read off the asymptotic conditional distribution of the number of events in the first k that occur. Again, everything is conditional on E0 epsilon n. Okay, and that is from this we get by continuous mapping theorem. It's a measure nu which depends on capital K and epsilon. We're looking at for a fixed k and epsilon positive. Okay. Now, keeping epsilon fixed, which we will let capital K go to infinity. Okay, so that's the total cluster size. So given that E0 epsilon n has occurred, I ask how many have occurred. Okay, and that's mu epsilon. But again, the order is important. I've let little n go to infinity and capital K go to infinity, because if I let little n go to infinity, then that would be infinity almost surely. So this, which is why I let them go to infinity in this particular order. So letting n go to infinity and capital K go to infinity makes precise that mu epsilon is the total number of events whose occurrence has been caused by the first deviation or the 0th deviation. And then we study the behavior of this as epsilon goes to 0, okay, under appropriate scaling.
I actually have a question. So
Yeah.
What is the quick intuition behind the fact that even already for j is 1, you could have a 0 indicator? So it means that because you have a very large sum and you just shift it by 1. Why does that not for n going to infinity simply doesn't make any difference?
Probability of E1 epsilon n given E0 epsilon n, it has a limit which is strictly between 0 and 1.
This is because you're short memory.
This is because we are short memory. This is because we are short memory. Yes.
Short memory.
Yeah. So for example, yeah, I have it on my slides. For IID case, the question is very easy to answer. I have it in a few slides down. Yeah. So that's because it has a short memory. It will be completely different in the long memory regime. Yeah. Okay. Okay, so let me go over the setup once again. So we have coefficients which are absolutely summable and their sum is non-zero. Since we'll be looking at deviations from mu, we can assume mu is zero without loss of generality. We assume that the distribution of the input random variables is not supported on a lattice. Okay, so in other words, the characteristic function has modulus strictly less than 1 everywhere other than 0. And we assume without loss of generality that this A is strictly positive, or else we could just multiply these input random variables with a negative sign and the edges as well with a negative sign. So these are the assumptions which, except the second one, neither is a loss of generality. Okay. Now this is a definition. So G theta is the probability measure obtained by exponentially tilting the distribution of Z naught by an amount theta. Okay, so I multiply the measure by e to the power theta x, and then this is just to normalize it so that whatever we have is a probability measure. And S naught is the right endpoint of the support of Z naught. And we fix an epsilon such that epsilon by A is less than S naught. So this is to ensure that the probability that we're talking about, E0 epsilon n, that is strictly positive. Okay. So for example, if epsilon is larger than this, and let's say if all the AJs were strictly positive, then this event would have been an impossible event. So, which is why we choose epsilon in this range. And in fact, that ensures there is a tau epsilon positive such that if you tilt by that amount, then the mean of that exponentially tilted distribution is epsilon by A. Simply because epsilon by A has been chosen to be inside the support, in the interior of the support. Okay, so these are random variables, a collection of independent random variables. We don't have to remember this at all. It's just various amounts of tilting is applied to various distributions. So I'll come to this Zj plus and Zj minus. This will play a role in defining the limit random variables. Okay, so just we need to remember that these are some. We don't have to remember the exact definitions. We just some amount of tilting is applied to the original distribution of Z naught, and these are obtained. Okay. And AJ is simply the partial sum of little a still j. Okay. Tau star be an exponential random variable with parameter tau epsilon by a, which is independent of all the random variables we have talked about so far. And then we define this new moving. I shouldn't call it the moving average because these are not identically distributed, but even minus and even plus are essentially the same thing as xn's, except you replace Zn by Zn minus and Zn by Zn plus. Like you define xn's except with these pluses and minuses. Okay. So this is the first result, which says that for a fixed epsilon in that range, so range means such that epsilon by a is between 0 and S naught, then this as a process indicator Ej epsilon and as a process converges weakly to V1 epsilon, V2 epsilon, etc. conditional on E0 epsilon, where Vj epsilon is simply the indicator that T star is larger than this thing, where Ey minus Ey plus, whereas in the last slide. So in order to understand this result better, it's imperative that we go over the IID case. Right, the overshoot. Yeah. So let's go over the special case of IID. So when x0, x1, etc. are IID, Vj epsilon is simply indicator T star is greater than this sum I running from 0 to j minus 1 yi minus yi plus. Here, these are now much easier to understand. So these are the ones with a negative sign are simply IID copies of x0, and ones with a positive sign are sampled from the tilted distribution of x0 such that the mean is epsilon. Okay, epsilon is a positive number. We just tilt it exactly by that amount, which gives us a mean of epsilon. And all these are independent of t star. So this is what you get if you just assume IID in the previous slide. So this is the underlying intuition. So for the sake of intuition, I've assumed IID 0 mean. So condition on the event that the sample of size n has the mean of the sample of size n exceeds epsilon, then x1 to xk, that converges vq to x1 star to xk star. But these are simply IID from a distribution obtained by exponential tilting xi by an amount, so that matches the mean. And like Sandeep already asked, the t overshoot is t star, which is an exponential random variable, again, which is independent of this x1 to xk star. So essentially, you are asking the question that in the sample, I am throwing out one random variable and introducing another random variable. That the new one I'm introducing is independent of whatever has happened. So it has a distribution the same as x0. And whatever I am throwing out, that, for example, I'm throwing out x1. Okay, that has a distribution x1 star. So the question is whether this difference x1 between x1 star and x1 that beats the overshoot or not. Okay. This is how precisely how the interplay between the overshoot and these random variables x1 star x1 comes into play. So this intuition kind of makes clear the why the result we had a couple of slides back is true.
The old random variables had memory, they were twisted. The new random variables are untwisted.
Right, in the same way. So now for random variables from the moving average process, you're essentially tilting the input process. Okay, the tilting happens at the level of the input process. And again, the tilting has to be such that the mean matches with whatever we want. Okay, so that was step one. The next step is we study the limiting cluster size. So as I said, after letting n go to infinity, we look at the sum up to k and then let k go to infinity. So that's something we call the limiting cluster size, d epsilon. So this is finite almost surely, which was clear from the expression as well, because we had a kind of a random walk and a t star. The random walk had a drift, so eventually it will exceed t star. So the next question that we ask is, how does this total cluster size behave as epsilon goes to 0? So for every finite epsilon, the total cluster size is finite, but of course it grows with as epsilon goes to 0. So at what rate? So d epsilon is like the typical size of d epsilon is like epsilon to the -2. And in other words, epsilon square times d epsilon has a limit, which is this quantity. So sigma z square is simply the variance of the input random variables. T naught is a standard exponential random variable, and this is a Brownian motion independent of T naught. So once again, this is something, this follows from, essentially follows from Donskoy's theorem, because what we have several independent random variables, we're adding them up. So it follows from essentially follows from Donskoy's theorem. So the question that you can ask me is, this limit depends only on sigma z square. Okay? So no other parameter involving the process xn is there in the right hand side. Whereas the first theorem that I showed you that had all these random variables zn plus, zn minus, they were exponential tilted versions of z naught. So there, the exact distribution of z naught was important. Whereas for this result, we only have the variance. Why? Why is the dependence on the distribution going away? The answer is, for a fixed epsilon, this is a large deviation event, okay, because the variance is of the order of n. So this is exactly a large deviation event. And hence, like I already said, large deviation result depend on the entire distribution. But then when we make epsilon go to 0, it doesn't remain a large deviation event anymore. It becomes a moderate deviation event, which is why the final limit depends only on sigma z square, nothing else.
So, Arijit, a question for you. Can one tease out something between moderate deviation and large deviation so that the other moments also become important? You don't just go straight from second moment to moderate.
So what I haven't thought really about this particular question, but for example, if epsilon goes to 0 along with n, then you can. My guess is you can see a regime above which you'll see a large deviation behavior, below which you'll see a moderate deviation behavior. But I'm not sure. No, but for that matter, I mean, when you look at large deviation, you look at all the entire distribution. So the moments.
But you kind of say the third moment is important, but after that doesn't matter.
Oh.
Fourth moment is important, but after that doesn't matter. Something like that.
So this is what I said, as epsilon goes to 0, this becomes a moderate deviation event, and hence the dependence is only through its variance. Okay, so quickly I'll tell you what happens for the Gaussian process. For the Gaussian process, the definition of short memory was a bit wider. Yeah, so this is slightly more general than the definition we have. Of course, if this happens, then it has moving average representation, but not really in the sense that we talked, because we looked the coefficients A0, A1. We didn't talk about negative coefficients with negative AJs. Okay, so which is why this is slightly more general than the setup of the moving average process that we talked about. So for Gaussian process, all these results are valid. Okay, for in the short memory Gaussian result. Short memory Gaussian process. So this is exactly the results I showed you for moving average process. So once again, this depends only through its variance, which is what we expect. And for Gaussian process can be studied only in terms of collision. Okay. So now I'll be moving to the long memory regime. So in long memory regime, Zn's are as before, and I start with coefficients AJ, which decays like j to the negative alpha. Alpha is between half and 1, and let xn be constructed from these as before. So in this regime, it turns out that for any j, conditional probability of EJ epsilon n given E0 epsilon n is 1. In other words, if you do the kind of cluster analysis we did, then we'll see that infinitely many of these occur due to the occurrence of 1, okay, in the limit. So in the limit, Vj epsilon n's will be 1 almost surely for all j. So the cluster analysis that we did in a short memory regime does not make sense anymore. We now have to ask the question, for a finite n, we have to look at how many of them occur and do something to that. And before I go into the precise question that we ask in the long memory regime, let me tell you the reason for this difference, because now this is a moderate deviation event. Because the variance of this partial sum is much larger than n. Okay, hence it's a moderate deviation event. So the variance being much larger than n makes it a moderate. So what we look at is the persistence time. That is, we look at the first j for which Ej epsilon n does not occur. Okay, for a finite n, I define In epsilon to be the first time for which the event doesn't occur. So, but by whatever I told you, I and epsilon will go to infinity almost surely, conditional on this, because it will be larger than any j eventually. So it has to go to infinity almost surely. So the question we ask is, at what rate? At what rate this guy goes to infinity? Okay, so for the long memory regime, we need a few more assumptions than in the short one. The sequence an is eventually non-increasing. So an is like n to the negative alpha. So which means it goes to 0 from the positive side. I assume furthermore that there is an integer n naught after which this is non-increasing. This is the old assumption. Is from a. We assume furthermore that if you tilt it by theta and take a supremum of theta mod theta less than equal to theta naught for some positive theta, then the variance of this distribution is finite. Okay, so I have a t square here. This is finite. So in other words, what I mean is if you look at the tilted distribution and the characteristic function of that, look at the modulus of characteristic function multiplied by t square, that is well. This is finite for some theta not positive. Another assumption that we need is that the first kappa moments of z naught match with the corresponding normal distribution. Sigma z square is simply the variance, where kappa is this guy. Okay. So the point to note is as alpha approaches 1, kappa goes to infinity. Okay, but for alpha strictly less than 1, the kappa is a finite number. I hope to be able to tell you why we need this assumption. I'm just in a hand waving way towards the end of the talk. Okay, so for stating the result, we need a few more notations. So beta and h are these numbers. Beta is a number between 0 and 1. H is a number between half and 1. T naught standard exponential random variable, and BHT is a fractional Brownian motion independent of T naught. That is, it's a zero mean Gaussian process whose covariance structure is given by this. So in particular, if h equals to 1/2, you get back the usual Brownian motion. And a few more definitions. So C is this number defined here. Sigma z square, as I've already told you, is the variance. And tau epsilon is the hitting time of the fractional Brownian motion, which has been shifted by this exponential random variable. This is independent of BHT. So the result is that if you scale the persistence time I and epsilon by n to the beta, then conditional on E0 epsilon, it converges to tau epsilon. And this tau epsilon is the hitting time we defined on the last slide. And it's unsurprising that this limit depends on Z not only through its variance, because now we are essentially in a moderate division regime. So I just want to go to the previous slide once more, because this tau epsilon is essentially this is something we should remember, because I have a few more slides showing you how we get to this tau epsilon. Okay, tau epsilon is the first time BHT gets below this number, and this is random. Okay. So I'll just briefly show you how we get to this tau epsilon. So SNJ is the process shifted by mean process shifted by J. Okay, so sample mean of the n observations starting from J. So what we show is conditional on E0 epsilon n. If you look at Sn and scale time by n to the beta, and this minus Sn0, then with this particular scaling, you conditionally on this event, you have this convergence. Okay, convergence to a drifted fractional Brownian motion. Okay, this is a deterministic drift. Okay. And this argument is very similar to that in the short memory regime. This is nothing but the overshoot. Okay, Sn0 minus n epsilon, except that now the size of the overshoot has changed. Okay, the overshoot is like, if you bring it over, overshoot is like n to the 2 minus 2 alpha. So with this particular scaling, Sn0 minus n epsilon, this converges to C by epsilon T naught. T naught is a standard exponential random variable. Standard exponential random variable independent of the fractional Brownian motion we are working with.
There's no memory-less interpretation.
Sorry?
There's no memory-less interpretation.
No, except that the size depends on. So earlier the overshoot was without any scaling when to converge to standard converge to exponential, but now you need a scaling.
You know what I'm saying? Whenever you see an exponential random variable, you try to think of memory-less.
Oh, memoryless. Not that I can think of at the moment. Now, if you just combine these two, I mean, you just simply add these two, then what you get is this minus n epsilon, this converges to, and asking for the first time where the event doesn't occur is essentially asking for the first time where this process goes below n epsilon. Okay, so once this can be shown in the right topology, we can apply continuous mapping theorem to argue that n to the so time is scaled by n to the beta, so n to the negative beta times the persist time converges to tau epsilon. So a couple of remarks over here. So the fractional Brownian motion we defined, that's a self-similar process. It has a parameter, self-similarity parameter is h. So which makes that the first hitting time tau epsilon has the same distribution like epsilon to the power minus 1 over h tau. In other words, what you can think of is that if you kind of look at the cluster till the first hitting time, that's of the order epsilon to the power minus 1 over h. Now, this should be compared with the analogous result for short memory regime, but the cluster size was like epsilon to the power minus 2. So, in other words, as alpha approaches 1, that is, we are approaching the short memory regime, then beta goes to 0 and h goes to 1/2. So h goes to 1/2 means we are back in the Brownian motion. So there's kind of a continuity over there. So growth rate of I and epsilon becomes slower and the fractional Brownian motion approaches the Brownian motion as alpha increases to 1. So why we needed additional assumptions for the long memory regime? The behavior in the model deviation regime is like that of central limit theorem. Okay, so essentially extend the central limit theorem in a certain way. I'll talk about it in a moment. And in the short memory regime, the standard Berry-Esseen theorem was good enough for us to give an estimate of the distance from normality. But in the long memory regime, that was not good enough, okay? Which is why we needed additional assumptions. And hence, matching the first few moments helped us proceed like in Edgeworth expansion to get the required amount of closeness between Gaussianity and the distribution of the partial sum. So the deviations in this case are moderate, and hence the variance depends only on the behavior depends only on the variance. The total cluster size, if we ask this question like in short memory regime, is infinity. fluctuations are now governed by a fractional Brownian motion as opposed to a Brownian motion, and we needed additional assumptions for technical reasons. So let me show you one computation which is kind of elementary, but nonetheless it makes it clear why we needed the additional assumption. So let's consider for the sake of simplicity IID random variables. And let's say for some n much larger than the standard deviation, square root n, we want to understand probability Sn greater than n, where Sn is simply the sum of x1 to xn. So what we first do is we tilt by an amount theta n such that the tilted mean is an by n, okay? So that when we add n random variables, we get a mean of exact an. Now, of course, the size of theta n will depend on an, which I'm not going into at the moment. But such a theta mean exists the moment as long as this probability is positive. And Fn is the measure obtained by tilting the distribution of x1 by an amount theta n. And let xn1 star, xn2 star be IID from Fn. So what we do is we look at the partial sum and center by the mean n. So Sn star is now a sum of zero mean random variables. And this is the standard computation. So probability Sn greater than n is, we integrate this indicator function on the with the distributions of x1 to xn. Now we divide and multiply. So over each of these we multiply by e to the theta n x1, e to the theta n x2, e to the theta n xn, and then we divide by the same thing. And the reason we do this is, if you recall, this is nothing but integrating with respect to the tilted distribution with a scaling. Okay, so this is the tilted distribution except the normalization. If you bring the normalization outside, then this becomes Fn dx1, and if you multiply all the normalization together, then you get expectation of e to the theta n Sn, because the normalization for this was just expectation of e to the theta n x1. Okay, so this is the remaining things are as they are. So in other words, now that we have everything in terms of Fn, this is nothing but the distribution of xn1 star, xn2 star, xnn star. So we can write in terms of those. So this is expectation of e to the power minus theta n star, this partial sum, indicator, this is greater than an. So what we do is, now an is the mean, which makes this event typical. Okay? An is the mean of this. So in other words, if Sn star is a sum of zero mean random variables, so now this becomes a typical event. Okay? Now, by definition, Sn star is the sum of IID zero mean random variables. So plain and simple, Lindeberg central limit theorem tells us that after scaling, it will go to standard normal. Now, what we do is we use Berry-Essen type bounds to estimate the error incurred when we replace this by a normal random variable of the same variance. Okay. Now, this is exactly where in the long memory regime, the estimate we needed was stronger than what Berry-Essen type bounds gave us, which is why we needed to assume the first few moments match that of Gaussian so that we could have the desired estimate. This is in a way the reason for the additional assumption of the first few moments matching that of normal. I don't think so. At least I don't know of a way of relaxing that. Okay. So this was a main ingredient in all the proofs, the long memory regime, the short memory regime. Yep. the future work. So one can ask, so of course for fixed n, this would go to n in probability because all of these go to 1. So is there a way to scale this such that we have a limiting distribution which is non-degenerate? Okay. That is something we haven't thought about yet, but that's a natural next question. So another future question is in the negative memory regime. So remember, in the short memory regime, we assumed the coefficients to be summable and the sum to be non-zero. But what happens when the sum is 0? So in this regime, probability of all of this, the conditional probability goes to 0. Okay, this is exact dual of what happens in the long memory regime. The long memory regime, all these conditional probabilities go to 1. Okay, here even if you look at the first one, that goes to 0. So in this case, even what's the right question to ask is a bit mysterious at the moment. And in the negative memory regime, this is a huge deviation event because now the now the variance is much smaller than little n, which is the order of the deviation. And much less is known about huge deviations than about large deviations and moderate deviations, which is why this is a more difficult problem than the ones we have already studied. So my student Bodhisattva Das is thinking about some of these problems. So, and these are the papers on which the talk I gave was based.
Any questions?
Yeah. So what is the quick intuition around behind this parameter beta? So if you would say on the envelope thing, because the beta tells you how many events enter the beta event you happen. So you had a formula. What was it? 4 minus 4 alpha over 3
Let me
minus
go
2
to that
alpha.
slide, and that will actually explain. So. Yeah. So beta is the parameter. Beta is the parameter which makes the magnitude of these two the same. The deviation from Sn naught and the overshoot. So if you choose beta anything else, then one of them will kill the other. So n to the power beta is the parameter which makes the magnitude of these two the same.
But basically, it relates to the how long you
how long you should be able to see in the future, so that so you're essentially scaling time, so that again you're scaling time in such a way such that these two, the magnitude of these two are the same. The overshoot, you're comparing the overshoot with the deviation from Sn0.
Any other question?
Just a comment. So I think Paul Dupuy and maybe Jose Blanchard and Glenn, they do some of this work where the twist that you do, the exponential twist, is now state dependent. So you see where you are and you see how much you have to go, and now you match the means. So I wonder if you can get more leverage from that, doing some of the analysis. Anyways. Okay, definitely we'll try.
Any more questions?
I have another question from you. So this negative thing will be really tricky because even there are sort of standard large deviations, not the ones that you say your cascade question, but even standard would be tricky.
Right. Simply because the variance is much smaller than n. Yes. So I don't know. We need to have more assumptions about the distribution of Z0. For example, I don't know. I'm just. infinitely divisible distributions would be a good starting point, but we haven't made progress in that direction.
Any more questions? Okay, if not, let's thank Arijit once more.